everyone, this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll be discussing about combinational logic circuit and various types of combinational logic circuits like adders and subtractors. And again in the adders, we'll be discussing about half adder, full adder, and subtractor, half subtractor and full subtractor, and comparator will be covered in another lecture. So in this lecture, we'll mainly concentrating on adders and subtractors. So first of all, let us see what is a combinational circuit. So basically, the digital logic circuits are classified into two types, that is combinational logic circuits and sequential logic circuits. So again, the sequential logic circuits are classified into two types, that is synchronous sequential circuits and asynchronous sequential circuits. So based on the output, we are based on the dependency of output, we are classifying the digital circuits majorly into two types, that is combinational and sequential circuits. So first of all, let us see what do you mean by combinational circuit. And here, a circuit in which different type of logic gates are connected is known as combinational logic circuit. And also, the output of combinational circuit is determined from the present combination of inputs regardless of the previous input and also the output. So the output mainly depends on the inputs applied to the circuit at that particular instant of time. It won't depend upon the previous input as well as the previous outputs also. So these are said to be combinational circuits. So combinational circuits are the digital circuits in which the output depends only on the present input. It won't depend on the previous output as well as previous input. So as it is not depending on the previous output or previous input, so it does not require any memory unit. Where if it is depending on, if the present output depends on the previous output, we need to store the previous output for further use. So for storing that, it requires memory element, as we don't have any dependency of output on previous output as well as the previous output is also known as present state as well as the previous input. So we don't require any memory element in the designing of combinational logic circuits. So the input variables, logic gates and output variables are the basic components of the combinational logic circuit. There is no feedback provided between the output and input, and also there is no memory element in the combinational circuit. It is only consisting of input variables, logic gates and output variables. And some of the examples of combinational logic circuits are adder, subtractor, decoder, encoder, multiplexer and demultiplexer and so on. So these are all the examples of combination logic circuit in which the output depends only on the present input. Present input in the sense the input applied to the circuit at that particular instant of time. So there are some characteristics for the combination logic circuit. Let us see what are the characteristics of combination logic circuit. At any instant of time, the output of the combinational logic circuit depends only on the present input terminals. That is the first major characteristic of combinational logic circuit. It won't depend upon any other parameters other than present input. And the combinational circuit does not have any backup or previous memory because it does not require any previous state or previous inputs to be stored. So that is why it does not require any backup or memory element. The present state of the circuit is not affected by the previous state of the circuit, previous state or the input. So the n number of inputs and m number of outputs are possible in combinational circuit. That means I want to say that we have m number of inputs, n number of inputs as well as m number of outputs. We can have any number of inputs as well as any number of outputs. So that is the combinational circuit. These are the major characteristics of combinational logic circuit. And this is the block diagram of combinational logic circuit, where we don't have any backup or memory element connected between the output and input. Only we have input variables as well as output variable. As I said, combinational circuit may have n number of inputs and m number of outputs. So n and m may be any integer, right? So these are the n input variables and these are the m output variables where it does not have any feedback or memory element. So this is the basic block diagram of combinational logic circuit. So these are n input variables and these are the m output variables, and this is a block diagram of combinational logic circuit. So the first category of combinational logic circuits is adders. As the name itself indicating that adder is a combinational circuit which can add the binary data, which can perform the addition of binary numbers. So here we have two types of adders. The first one is half adder and the second one is full adder. So based on the number of bits that the adder circuit is adding, the adders are mainly classified into two types, half adder and full adder. So half adder, now let us see, half adder is a combinational circuit which can add 2 bits of data, 2 bits of binary data at a time. Whereas this full adder is a circuit which can add 3 bits of data at a time. Now let us see in detail about half adder, full adder. So first of all, half adder. So half adder is a building block, basic building block of adding 2 numbers as 2 inputs and produces 2 outputs. So here, as you know that whenever we are performing addition, what are the 2 possible outputs we can have? That is, one is the sum and the other one is carry. And the other one is carry. 2 possible outputs are there, and as it is a half subtractor, it can add only 2 bits of data at a time. So we can define the half adder as a basic building block of combinational circuit which can add 2 bits of binary data and can produce 2 outputs. One is sum and the other one is the carry output. So for example, we have binary addition. Let us consider these are the 2 binary numbers 0, 0, 0, 1, 1, 0, 1, 1. Now whenever you are adding 0 plus 0, it is not logical addition, it is binary addition. Binary addition is different from logical addition. In what sense a binary addition is different from logical addition, I will tell you now. So here 0 plus 0 is 0, 0 plus 1, 1, 1 plus 0, 1 and 1 plus 1. 1 plus 1 is in decimal it is 2. Whereas in binary it can be represented as 1, 0. 2 in binary can be represented as 1, 0. So 0 is the sum and 1 is considered to be carry. So that is how I can say that whenever we are adding 2 bits of binary data, we can have 2 possible outputs. One is the sum and the other one is a carry. Whereas coming to the logical addition, so this is binary addition, right? So now coming to the logical addition. Logical addition is performed by a logic gate R. Okay, that you know. 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1. Whereas 1 plus 1 is also 1. This is logical addition and this is the binary addition. So half adder is a combinational logic circuit which can perform the addition of 2 binary numbers. Okay. So and we have 2 inputs and 2 outputs in case of half adder. So this is the block diagram which is showing the number of inputs and number of outputs of this circuit, and the inputs are denoted by AB, whereas the outputs are represented as sum and carry because we have 2 possible outputs. So the adder is used to perform OR operation of 2 single bit binary numbers. The augment and addend bits are 2 input states and carry and the sum are the 2 output states. So here whenever you are performing A plus B, we will be representing. So this B is known as addend. This B is known as addend bit and this A is known as augment bit. Okay. So the number which is to be added is called as addend. Then to which the number is added is called as augment. So A is augment and B is addend, and we have 2 possible outputs, sum and carry. So that is the half adder block diagram. So as we can have 2 inputs and 2 outputs, so we can draw the truth table. So it just performs the addition, binary addition. So the truth table of this half adder can be, so truth table, you all know that truth table is a tabular column which represents the possible input combinations for which the output is denoted by. So 0 and 1. So here this is showing us the truth table always gives us the output values for all the possible input combinations or else for all the combinations of input variables. Okay. So as we have two inputs here, we can have how many input combinations? 2 parent, that is 2 power 2 is 4. So these are the 4 combinations of input 0, 0, 0, 1, 1, 0, 1, 1. Now I am performing the addition. So as we all know that the rules of binary addition, 0 plus 0, 0 with a carry 1. Two outputs we have represented, sum and carry. So when we are adding 0, 0, sum is 0 and carry is also 0. 0 plus 1, sum is 1. Do we get any carry? No. So carry output is 0. 1 plus 0, again the sum is 1. Carry, we don't have any carry, so that carry bit will be 0. 1 plus 1, so 1 plus 1 is 0 with a carry 1. So the sum becomes 0 and the carry becomes 1. So this is the truth table of half adder. So according to the truth table, we can see that A and B are the input states and sum and carry are the output states. The carry output is 0 in case when both the inputs are not 1. Okay, when that means the carry output is 1 only when both the inputs are equal to 1, and it is 0 if both the inputs are not equal to 1. The carry output is 0. So the least significant bit of the sum is defined as the sum bit, and so that means we can say that as the sum output is 1 if at least one of the input is equals to 1, and it is 0 when both the inputs are same. That is when both the inputs are either 0 or equal to 1, the sum output is 0. And the carry output is 1 when only both the inputs are equal to 1, and in that case only carry output is 1. In all the other cases the carry output is 0. Now based on this, I could write the equation for sum and carry. So the sum output is 1 for two combinations 0, 1 and 1, 0. The combination 0, 1 can be represented as a minterm as A is 0, we can represent it as A bar, and B is 1, so B. Whereas this combination as a minterm can be represented as A, B bar. So for these two combinations, the sum output is 1. So that is why I can write the sum output as A bar B plus A B bar. And similarly, the carry output is equals to 1 only for one combination, that is when both the inputs are equal to 1. So and hence I can write down the minterm for this one as AB because A and B are equal to 1. So this is this one. Or else you can also take a K-map, two variable K-map, because why to take two variable K-map? Because we have only two variables here, two input variables AB 0, 1, 0, 1. So this is for sum. Let us consider when the sum output is 1. So for 1 and for 2. I told you that diagonal adjacency is not possible. So we can just take these as it is and write down the minterm or else prime implicant for this one. So for this cell A is 0, B is 1. So A bar B. And for this cell A value is 1, B value is 0, A B bar. So sum is equals to A bar B plus AB bar. So if you look at this expression, I can write this one as A XOR B because A XOR B is equals to A bar B plus AB bar. Okay. And some carry output is only 1 for one combination. So no need to draw the K map. Directly I can write down the prime implicant as AB. So carry output is AB. So now we have got the Boolean functions here. So these are the Boolean functions. So carry output is A dot B, whereas sum output is A XOR B, which is equals to A bar B plus AB bar. So this is the logic diagram for half adder. So where we require, in order to implement the half adder, sum to get the sum, what I want to use, I have to use XOR gate, and for get the carry output of the half adder, I have to use the AND gate. So to implement this half adder using logic gates, I require a 2-input XOR gate. So this is a 2-input XOR gate to which the inputs are applied as A and B, and a 2-input AND gate. Again the inputs are taken as AB. So the C out or else the carry output is given by A dot B, and the sum output is given by A XOR B, which is equals to A bar B plus AB bar. So this is the logic diagram of half adder. So what we can see, so here we can observe that this half adder can be used to perform the addition of 2 bits. So for example, let us consider I'm adding 2 binary numbers. Okay, so which can have more than 2 bits, 110, 111. So these are the 2 numbers. I'm performing the addition. So in this case, so this addition can be done by addition of 2 bits can be done by a half adder. So 0 plus 1 is 1 with a 0 plus 1. So 1 plus 1, 0 with a carry 1. So now here I need to add 3 bits at a time. Here I need to have 3 bits at a time. So instead of having a 2-bit adder, if I have 3-bit adder, I can add 3 bits. 2 are the bits from the numbers and 1 is a carry from the previous section. So let us consider this is the carry in. So that means half adder can perform the addition of 2-bit binary numbers only, whereas 2 bits only, whereas in some cases we need to add 3 bits of data at a time. So in such cases I cannot use the half adder because half adder can add only 2 bits at a time. So for that purpose, I am going for another adder circuit, which is nothing but full adder, where the full adder can add 3 bits of data. That is, 2 bits are the bit A and B, and the other bit is the carry input from the previous section. So that is a major drawback of half adder. So half adder cannot perform the addition of 3 bits. It can perform only the addition of 2 bits at a time. Whereas in some cases we need to add 3 bits at a time also, where half adder is failing to do that. So that is why we are going for the full adder. The half adder is used to add only 2 numbers. To overcome this problem, the full adder was developed. The full adder is used to add 3 1-bit binary numbers A, B and carry input. A, B and carry input. So the full adder has 3 input states, that is A, B. Cin is a carry from the previous section and 2 output states, sum and carry. So this is the block diagram. We have 3 inputs here, A, B and Cin, and 2 outputs, sum and carry. So that means what I can say, a full adder is a combinational circuit which can add 3 bits of data at a time and can produce the 2 outputs, that is sum and carry output. So now let us see the truth table of this one. So what I can say, full adder is a 3-bit adder. So how many inputs we have here? 3 bits. So now how many possible input combinations we have for 3 input variables? 2 power 3, 8. So this is the truth table which is listing all the 8 possible combinations of input and the respective sum and carry output for this 3-bit addition. So A, B, Cin, sum and carry. A, B, Cin are the inputs and sum and carry are the outputs. So just write down the 8 possible input combinations here. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. So these are the 8 possible input combination. Now I am performing what? So I am performing A plus B plus Cin. So now 0 plus 0, 0, 0 plus 0, 0. Sum is 0, carry is also 0. Now again 0 plus 0, 0, 0 plus 1, 1. So 1 is a sum and do we have any carry? No, we don't have any carry. So the carry output is 0. Now again coming to this combination, 0 plus 1, 1, 1 plus 0, 1. So sum is 1. Do we have any carry? No, so that is why carry output is 0. Now 0, 1, 1. So 0 plus 1, 1. 1 plus 1. As we all know that 1 plus 1 is producing the sum output as 0 and carry output as 1. So that is why 1 plus 1, 0 with a carry 1. Sum is 0 and carry is 1. Now 1 plus 0, it is 1. And 1 plus 0 again, it is 1. So that is why carry output is 0. Now coming to the 1 plus 0, 1. 1 plus 1, 0 with a carry 1. So the sum output is 0 and the carry output is 1. Now 1, 1, 1, 0. 1 plus 1, 0 with a carry 1. So we have already got the carry here. So the sum is 0. 0 plus 0 is 0. Sum is 0, carry is 1. Now coming to this one, 1 plus 1, 0 with a carry 1. So 0 with a carry 1. So I made carry output as 1. So 0 plus 1 is 1. So this is the truth table. So this is the 3-bit addition and it is called as full adder. So where A and B are the input variables and these variables represent the 2 significant bits which are going to be added. CIN, that is CIN, is the third input which represents the carry from the previous lower significant position, and the carry bit is fetched. Okay, so this is the truth table. So the sum and carry output, carry are the output variables that define the output values. The 8 rows under the input variables designate all possible combinations of 0 and 1 that can occur in these variables. So A, B, C are the input variables and all the 8 possible values are the all the 8 values in as rows represent the possible combinations of input. Now let us try to derive the equation for this. So first of all, we have, so now I am deriving. So how many variable K-map is required? How many inputs we have? 3 inputs. So that is why I require three variable function A, B, C, in. So the order in which is followed in the truth table, the same order we should follow in K-map also. 0, 0, 0, 1, 1, 1, 1, 0. This is 0, 1. Sorry, actually here we have to take A only, whereas here we have to take B, C. Right? Now sum output, I want to derive the Boolean function. Sum output is 1 for 1, 2, next 4, 7. 1, 2, 4, 7. 1, this is 0, 1, 3, 2, 4, 5, 7, 6. 4, 5, 7, 6. Okay. So now the sum output is 1 for 1, 2, 0, 0, 1 means 1. So 0, 0, 1. Next 0, 1, 0 means 2. Next 4, that is 1, 0, 0. And then 7. 7 is this one. So now, can I form the groups of any two adjacent cells? No. Are these two cells said to be adjacent? No. These are defined by more than one variable. Are these two adjacent? No. Are these two adjacent? No. Are these two adjacent? No. So that is why no adjacent cells are possible and hence no grouping can be done. So that the sum expression can be given by first expression A bar, B bar, C in, and the second one, this one for A is 0, A bar, and B value is common and C in complement. And for this one, A, next B bar, C in bar, plus this one, A, B, C in. This is the sum equation. Now let us try to derive the carry expression. So here the sum expression we have got it as A bar, B bar, C in plus A bar, B bar, A bar, B, C in bar, A bar, B, C in bar, A bar, B, C in bar, next plus A, B bar, C in bar plus A, B, C in. This is the sum expression. Okay, this is a sum expression. Now I want to derive the expression for carry. So carry, again I have to use 3 variable K-map. So the 3 variable K-map is A, B, C in, okay, A, B, C in 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, right? So this is for carry output. This is for carry output. Now let us see for which combination the carry output is 1. This is 3, 5, 6, 7. 3, 5, 6, 7. So this is 3, this is 5, 6, 7, right? So that is the expression here. So now I can say that these two are adjacent cells and these two are also adjacent cells and these two are adjacent cells. So now I can write carry output as, so what is the min term for this one? As A value is varying for these two, eliminate A, whereas B value and C in value are common, B, C in. And coming to this one, so A value is common for both of these cells, so consider A. Next, for these two cells, B value is common, whereas C value is varying, so consider only B. Now for this one, so A value is common for both of these cells, so consider A, whereas B value is varying and C in value is common, so C in. So carry output is equals to AB plus BC in plus AC in. So this is the equation. Okay. So now based on this, we can draw the logic circuit. So this is the logic circuit for the given, for the full adder, which can perform the addition of 3 bits. So I require now, so here we have this one, right? So now I want to simplify this one. I want to simplify this one. So here, now in these two terms, okay, in these two terms, I can take C in as common. So I can write it as A bar B bar plus AB. Next, again in these two terms, I can take C in complement as common. So C in complement, if I take it as common, A bar B plus AB bar, right? So now C in, now I can write this one as A XOR B plus C in complement of A XOR B. Okay, what is A XOR B? A XOR B is nothing but A bar B bar plus AB, which is nothing but A XOR B whole complement. So this is the thing we have seen. So now I can write it as C in into, let us consider A XOR B as W. So this one becomes A XOR B whole complement plus C in complement of A XOR B, right? So now I am considering this one. If I consider A XOR B as W, A XOR B will become W complement. So here C in into W complement plus C in complement into W. So I can write this one as C XOR W. C in XOR W, where W is nothing but A XOR B. So C XOR A XOR B. So I can rearrange the terms A XOR B XOR C in. So this is the logic circuit. This is for sum. This is for sum. So carry expression, anyhow we have got it as AB plus BC in plus AC in. I cannot further simplify this one. So that is why the logic circuit, to implement the sum, I require a 3-input XOR gate to which we have the inputs as A, B, C in. So that A, C in exclusive or A XOR B. And coming to the product and carry output. So this is A and B. So the output of the first AND gate is AB, whereas the second AND gate A, C in. A, C in. And the third logic gate is B, C in. So now I can write down carry output as AB plus ACN plus BCN. So this is the full adder which can perform the addition of 3 binary bits at a time. So now here we can implement a full adder circuit using one 3-input XOR gate and 3 2-input AND gates and 1 OR gate. So instead of doing this, I can also implement a full adder circuit using half adder, where half adder can be implemented using only one XOR and one AND gate. So like that, I can reduce the complexity. So how can we implement a full adder using 2 half adders? So this is the block diagram of implementing full adder circuit using 2 half adders. I am taking 2 half adder circuits. This is half adder circuit A, to which the inputs are given AB as the input, and here A XOR B. So A XOR B and C in are the inputs to the other full adder, so that the sum can be obtained. And similarly, we have sum output and we have carry output, right? So I'm taking the carry output of first half adder and the output of second half adder, and I'm giving it to an OR gate, so that the carry output, which can be given by AB plus BC plus AC in. AB plus BC in plus AC in, right? So this is the circuit. So now again, you know that a half adder includes 2 logic gates, that is 1 XOR and 1 AND gate. 1 XOR and 1 AND gate. This is our 1 XOR and 1 AND gate here. This is our sum and this is our carry output, right? So where A and this is B, A, B, right? So this is the circuit. So I want to implement that half adder using full adder using 2 half adders. So this is one half adder and this is another half adder where I can use an OR gate with that. So now we'll verify whether we are getting the same expression or not. Whether we are getting the same expression or not. Okay. So for that, what I'm going to do. So here, the output of this one is A XOR B. This one is A and B. So here, now what I'm getting, A XOR B XOR Cin. A XOR B XOR Cin. This is the sum output of full adder. Now coming to the carry output. So here the output of this AND gate is, this is A XOR B and this is Cin. Now let us apply this. So A XOR B into Cin. A XOR B into Cin and here AB. A XOR B into Cin into AB. So C out now becomes A XOR B into Cin plus AB. So now if I expand this one, so what I'll get, I will get it as A bar B plus AB bar into Cin plus AB. A bar B plus AB bar into Cin plus AB. Now if I expand this one, so what I'll get, A bar B Cin plus AB bar Cin plus AB, right? So now I'm going to take Cin plus Cin complement if I multiply with this. So let us do this derivation here. So A XOR B into Cin plus AB here. This is the carry output. So now I'm expanding this, A bar B plus AB bar into Cin. This is also Cin plus AB into Cin plus Cin complement, right? So now here what happens, A bar B Cin plus AB bar Cin plus AB Cin. So what I'm doing, I'm just multiplying this one with Cin plus Cin complement. So it doesn't make any change because we know that C plus C complement is equals to 1. So I'm just multiplying this one with 1. So plus AB Cin complement. AB Cin complement. So now in this case, what I want to do here is, I want to take B Cin. So in that B into Cin as common. So in these two terms, so I will get A plus A bar. A plus A bar. So A B bar Cin plus AB Cin bar. AB Cin bar. So here B Cin I will get plus A B bar Cin plus AB Cin complement. AB Cin complement. So now what I want to have, I want to take it as B Cin plus here A as common. So B bar Cin plus B Cin bar. Just a second. So here A as common, I am taking B bar Cin plus B Cin bar. B Cin bar. So B Cin plus A into B XOR Cin. Okay. So this I can write it as B XOR Cin. So I can have this expression for carry output, either this or this. So either of the way we can take. So either I can take it as BC or AB. Okay, either of the inputs I can apply to the first half adder, and the other input is given as the input to the next half adder, so that I'll get the sum and carry output. So this is the construction of full adder using two half adders. Now coming to the next, this is how we can implement a full adder using two half adders. And next, combinational logic circuits. The most important combinational logic circuit is subtractor. So again, the subtractors are classified into two types. What are those? Half subtractor and full subtractor. So as we have seen that half adder can add only 2 bits at a time. So this half subtractor can also perform the subtraction of 2 binary numbers, where full subtractor can perform the subtraction of 3 binary numbers. So here half subtractor is a combinational logic circuit or the basic building block for subtracting two binary numbers. It has, again, whenever you are performing subtraction, as we can have sum and carry output in case of adder, we can have two outputs, two possible outputs are there for subtraction also. That is difference output and borrow output. So, whenever you are performing subtraction, for example, let us consider a decimal subtraction 101 and 99. So, here I am subtracting these two. These are the decimal numbers. So, what we will be doing, I cannot subtract 9 from 1 because 9 is less. So, in that case, what I am doing, I am going to take a borrow. So, I cannot take borrow from the next digit because it is 0. So, then I have to take from the next digit. So, if I take borrow from this, it becomes 9 on the 0 and 10 on the 1. So 10 minus 9, it is 1 and 9 minus 9, it is 0. As we have taken borrow, only 1 is there on the digit, on this digit. This one has been given as borrow. So now it becomes 0, right? This is 1. So this is a subtraction process. So that means whenever we are performing the subtraction, this is called as difference, whereas this is called as the borrow. So, whenever you are performing the subtraction, we have two possible outputs. One is the difference output and the other one is the borrow output. So, two inputs and two outputs. And the two inputs are represented with A and B. And the two outputs are represented with the difference and borrow. So, this is the block diagram for the half subtractor. Two inputs and two outputs. Now, coming to the truth table, as we have two inputs, so four possible combinations we have. 0, 0, 0, 1, 1, 0, 1, 1. And coming to the outputs, we have two outputs, difference and borrow. So what I'm doing, I'm just performing A minus B. Whenever we are performing A minus B, that means B is subtracted from A. The number which is subtracted is called as subtrahend. And from which we are subtracting is called as minuend. A is said to be minuend and B is said to be subtrahend. So now I am performing A minus B. 0 minus 0. So 0, difference 0, borrow is 0. 0 minus 1. Is a subtraction possible? No, we should take borrow. So if I take borrow, the borrow becomes 1 here. If I take borrow from the next neighboring digit, so this one becomes 1 0 because it is binary subtraction. 1 0 means in decimal it is 2. 2 minus 1 is 1. So that means when we are subtracting 0 from 1, we need to take borrow. It becomes 1 0. 1 0 minus 1 is 1. Okay. And difference is also considered to be 1. So 0 minus 1 is difference 1 and borrow is also 1. Now coming to 1 minus 0, it is possible. I am subtracting 0 from 1. So difference is 1 and borrow is 0. And 1 minus 1. So 1 minus 1 is difference 0 and borrow is 0. We are not taking any borrow. So that is why borrow output is considered to be 0. So now this is the truth table. And from the truth table, I can say that the difference output is equals to 1 when either of the inputs are equal to 1. When both the inputs are same, the difference output is becoming 0. Coming to the borrow. So the borrow output is equal to 1 when the minuend is smaller than the subtrahend. That means when B is equals to 1 and A is equals to 0, in that case, the borrow output becomes 1. So this is the truth table. And now from this truth table, I can write down that borrow output is 1 for two combinations, that is 0, 1 and 1, 0. 0, 1 can be written as, the prime implicant for this one can be written as A bar B. This is A bar B, whereas for this one, AB bar, and hence the difference output is equals to A bar B plus AB bar. I can also write this one as A XOR B. Similarly, borrow output is 1 for only one combination, and for this combination, the prime implicant is A bar B, and hence this is the borrow output. So borrow output is given by A bar B, whereas the difference output is given by A XOR B. This is similar to the adder. Only the difference is we have carry output, we have here borrow output, and the borrow output is equals to A bar B. So based on that logic functions, we can implement that using one XOR gate which is having two inputs, one NOT gate to get the complement of A, this is A bar, and then a two input OR gate. Two input AND gate. So this is the half subtractor. So what is the output of this one? A XOR B. This is difference. And this is A bar B. A bar B borrow. So this is the half subtractor logic circuit. Now coming to the full subtractor. So again, similar to the half adder, the half subtractor is also can perform the subtraction of two numbers. But there is some cases we need to subtract three numbers at a time. In such case, we will be going for another circuit, that is full subtractor, which can perform the subtraction of three binary bits. Okay. So full subtractor is used to subtract three 1-bit numbers A, B, C, which are minuend, subtrahend and borrow. Whereas in full adder, what are the three bits? That is augend, addend and carry input from the previous section. Okay, borrow respectively. So the full subtractor has three input states now and two output states. So any subtraction can result two outputs. One is difference and the other one is borrow. So this is the block diagram of full subtractor. So three inputs A, B, borrow in and difference and borrow output. Now coming to the truth table, this is the truth table here. So as we have three inputs, we have 8 possible combinations 0, 0, 0, 0, 0, 1, 0, 1, 0 and so on 1, 1, 1. Now what we are doing? A minus B minus borrow in. Okay, B in. So now 0 minus 0, 0, 0 minus 0, 0. So difference 0, borrow 0. 0 minus 0, 0. 0 minus 1. Is it possible? No, we need to take borrow. So that is why borrow is 1. And if I take borrow, it becomes 1, 0 minus 1. So it is, difference is 1. Now 0 minus 1. So we have to take borrow. So the borrow input is 1. And if I take borrow here, this becomes 1, 0. 1, 0 minus 1 is 1. And 1 minus 0 again, 1. So the difference output is 1. And borrow output is also 1. And 0, 1, 1. So this is 0 minus 1. Borrow we have to take. So 1 minus 1 is, 1, 0 minus 1 is 1. 1 minus 1, 0. So that is why 0. And similarly 1, 0, 0. 1 minus 0, 1. 1 minus 0, 1. And the borrow is 0. 1 minus 0, 1. 1 minus 1 is 0. So that is why borrow 0 and difference is also 0. 1 minus 1, 0. 0 minus 0, 0. So the difference 0, borrow is 0. 1 minus 1, 0. 0 minus 1. So we cannot subtract 1 from 0. So that is why we need to take borrow. So that's why borrow output is 1 and difference output is 1. So this is the truth table. Now by observing this truth table, what we can say, the difference output is becoming 1 when the difference and borrow output variables A and B are the input variables. These variables represent the two significant bits that are going to be subtracted. Borrow in is the third input, which represents the borrow. And the difference and borrow output are the output variables that define the output values. So here these are all the combinations for which the difference output and borrow output are equal to 1. Now based on this, I want to draw the K-map so that the difference output equation and borrow output equation can be derived. So difference output is 1 for the combination. This is, let us consider 0, 0, 1 is 1. 0, 1, 0 is 2. Next 4 and next 7. 1, 2, 4, 7. Now coming to the borrow, this is 1, 2, 3 and 7. 1, 2, 3, 7. So here 1, 2, 4, 7 for the combinations 1, 2, 4, 7 difference output is 1. So this is the equation. This is the K-map for difference output. So 1, 2, 4, 7. Can I group these elements together? Can I group these any of these cells together? No, because all these are not said to be adjacent. So I cannot group them. I can take them directly. So this is the equation here. Okay. So this is the equation. So where I can write this one as A bar, B in. And this one I can write it as A bar, B in bar, which is borrow in bar. And this one I can write it as A, B, B in, because A is 1, B in are also 1. So whereas this one is A, B bar, B in bar. So these are the things that we have obtained. So this is the expression. Now coming to the borrow. So borrow output is 1 for the combinations 1, 2, 3, 7. So 1, 2, 3, 7. So I can group these two, these two, these two. I can form 3 pairs. By forming the 3 pairs, I can eliminate one variable. The prime implicant for this one is A bar B, whereas for these two cells, B is common, C is varying, eliminate, B in is varying, eliminate B in. And for this group, I can write the prime implicant as A is varying, eliminate A, whereas B in are common, B in are common. Now coming to this one, this is A bar because A value is 0, so A bar. Now for these two cells, B is varying, eliminate B. B in bar is common, which is B in is common, which is equals to 1, so B in. So now the equation is A bar B in plus A bar B plus B in. So this is the equation for B out. Okay. Now by simplifying this one, I can get the difference equation as A XOR B XOR B in. So this is what we can get. Whereas the borrow output can also be written as A bar B in plus A bar B plus B in. Or else we can also write this expression as A bar B plus A bar B plus A XOR B into B in. So this is the expression that we can write from this borrow output. Now the logic circuit for that full subtractor is this one. We require a 3-input XOR gate to which the 3 inputs are A, B, B in, and 3 AND gates here. So 2 AND gates are having A bar B are the input. So A bar B, and for this one again A bar is the input and then B in is the input. So A bar B in, and to this one B in are the input. So finally the output is equals to this one. So this is the basic logic circuit. Similar fashion of implementing a full adder using 2 half adders, we can also implement a full subtractor using 2 half subtractor. So this is the block diagram for implementing full subtractor using 2 half subtractor. This is half subtractor, this is 1 half subtractor. So first half subtractor is given with the inputs A, B, whereas the second half subtractor, the output of the first half subtractor, which is a difference output, is given as input to the half subtractor B, and the other input is B in, and here the output of this one and the borrow output of this one are given to the OR gate, so that I will be getting this borrow output. So this is the implementation here. So as you have seen that half subtractor includes 1 XOR, 1 NOT gate and 1 AND gate. So we are replacing that each subtractor with 1 XOR, 1 NOT gate and 1 AND gate. So this is 1 half subtractor which includes 1 XOR, 1 NOT gate and 1 AND gate. So what is the output here? A XOR B, whereas the other input is B in or borrow in. And now here this is what we are getting, this is A bar B we are getting, and here A XOR B is complemented here. So A XOR B whole complement, and the other input to this one is B in. And finally this is given here, and finally we are getting the borrow output. So this constitutes another half subtractor along with an OR gate represents the full subtractor. So this is the implementation of full subtractor using 2 half subtractors. So that is about subtractors. And now coming to the binary adder. So till now we have seen adders, so which can perform a addition of 2 bits or 3 bits at a time. For example, I want to perform an addition of 2 binary numbers of any length. Any length means not single bit numbers I want to add. I want to add 2 binary numbers of more than 1 bit each. So in that case, how can I perform the addition? So in that case, I can go for the binary adder. So binary adder is a logical circuit which is used to perform the addition operation of 2 binary numbers of any length more than 1 bit each. So the binary adder is formed with the help of full adder circuit. The full adders are connected in series, and the output carry of the first adder will be treated as the input carry of the next full adder. So here, like that, we can implement. So for example, here for example, let us take two binary numbers 110 1001. These are the two binary numbers which are 4-bit each. Now how can we perform the addition? We need to perform the addition bit by bit, starting from LSB to the MSB. For performing these two, I can use a full adder or half adder. Why I can use a half adder? Because these are the least significant bits. So as we don't have any carry while adding the least significant bits, so I can use a half adder. Or else I can use a full adder by considering the carry input as 0, because we have 3 inputs, but we have only 2 bits here. The other input, which is the carry input, is considered to be 0. That means in the least significant section, I can use either a half adder or a full adder. Again, for this, I have to use full adder because we may get a carry from this previous section. So in that case, I need to add even the carry also. Such case, I have to use full adder. This also I have to use full adder. This also I have to use full adder. For 1-bit addition, I require 1 full adder. So like that, in order to implement an adder circuit which can perform the addition of 2 4-bit binary numbers, I require 4 full adders, or I can have 1 half adder plus 3 full adders. Like that also we can implement. Okay, like that, depending on the number of bits in each number, I can use that many number of full adders which are connected in series in order to perform the addition. Okay. So now 1 plus 1, 0 with a carry 1. Now in this case, I need to add 3 bits, so I have to use a full adder. So 1 and then 1, 0. So in this case, carry input was not there, so we have to consider it as 0. So 0 plus 1, 1, 1 plus 0, 1. 1 plus 1, 0 with a carry 1. This is our carry output. Okay, this is our sum output. So whenever you are performing the addition, the carry output is a single bit addition, single bit output, whereas the sum is having number of bits which is equal to the number of bits of each number. So as we have 4-bit binary numbers here, so the sum is also 4-bit. So we have only carry output which is equals to 1 bit. Okay. So now let us design an n-bit binary adder. So if you want to add 2 n-bit binary numbers, I require to connect 2 n full adders in series, such that the carry output of one section is given as carry input to the next section. Okay. So this is the n-bit parallel adder. So the number of bits decides the number of full adders to be used in parallel adder circuit. So here why we are calling it as parallel adder? Because all the inputs are applied at a time parallelly to all the full adders. So that is why it is called as parallel adder. 4-bit binary parallel adder circuit is shown here. This is the circuit diagram of 4-bit binary parallel adder. Okay, where all the bits are applied at a time. So full adder, this is a full adder circuit. As we know that full adder is having 3 inputs. So A0, B0 are the inputs here. So for example, A here, A3, A2, A1, A0. Now B is B3, B2, B1, B0. We are performing the addition of these. Okay, so that means for the first full adder, I have to give the 2 inputs A0, B0. Okay, whereas the carry input is considered to be 0 because the least significant bit. When we are adding least significant bits, we don't have any carry. So in that case, carry input is considered to be 0. So by addition of these two will produce the sum output. If carry output is given, that is given as the carry input to the next full adder. Okay, whereas the other 2 inputs of next full adder or else full adder 1 is A1, B1. And by adding A1, B1 and Cn, it produces the sums S1 and carry. That is the second bit of sum. and then again this carry is given as input to the next one, and the 2 bits of the 2 numbers A2, B2 are given as inputs. It produces the sum. If the sum and carry, if the carry is 0 or 1, carry may be either 0 or 1, that will be given as input to the next full adder. A3, B3, sum S3 and C3. So like that, we can design an n-bit parallel adder by cascading or else by just connecting the n number of full adders in series, such that the carry output of first full adder is given as the carry input to the second full adder, and so on. Okay, and finally the carry output is taken from the last full adder, which is the 1-bit carry output, and from all the full adders we can take n-bit sum. So whenever you are performing n-bit addition, okay, whenever you are performing the addition of 2 numbers of n-bit each, it produces n-bit sum as well as 1-bit carry, 1-bit carry output. So here, as I told you that I can simply even replace this half full adder with half adder, with which is having only 2 inputs. There we don't consider any carry input, which is to be taken as 0. So this is the full adder circuit, binary full adder circuit. Similarly, we can also implement subtractor. We can also implement binary 4-bit binary subtractor also. How can we implement binary subtractor? So what we are doing, A minus B we are performing, where A is A3, A2, A1, A0, B3, B2, B1, B0. As it is minus, so minus means, so as we know that the subtraction can be converted into addition by taking the complement of B, either 1's complement or 2's complement of B, right? So that means by converting this negative number into positive number, by taking its complement, either 1's complement or 2's complement, we can convert the subtraction into addition. So that means I can use the same circuit for the binary subtraction also. Only the thing is, need to get the complement of B. How to get the complement of B? By just adding an inverter. By just adding an inverter to each input, that is B input of each full adder. So what it will do, if I add an inverter, so before applying that particular bit B to the full adder, it is getting complemented. Inverter performs the complementation operation, changes zeros to ones and ones to zeros. Changing the ones to zeros and zeros to ones is nothing but getting the ones complement. So ones complement of a negative number will give you positive number. Now it will be added together. So that we can also implement the binary subtractor using the same circuit. Only the difference is all the B inputs are applied to the inverter before applying them to the full adder circuit, such that the subtraction operation is converted into addition by getting the complement of negative number B. Okay, and inverters are mainly used to get the complement of the number. So this is how we can implement parallel adder and parallel subtractor. So what are the drawbacks that we can observe here? Even though all the inputs are applied at a time, do we get the outputs all at a time? All the sum bits are available at a time? No, because there is some delay that is due to the propagation of carry output of one section to the carry input of the other section. So even though we are applying all the inputs at a time, what is happening? This will take some time due to the propagation delay of logic gates. Instantaneously, when we apply the input to the logic gate, it will never produce the output. It will take some time. So due to that time, it is delayed and it will be applied to the next stage. So this delay is known as propagation delay. So even though all the inputs are applied at a time, all the 4 sum bits are not available at a time due to the propagation delay of the carry, which has to propagate from one stage to the other stage. So that is only the thing that we can observe from the 4-bit binary adder or subtractor. Okay, so that's all for this lecture. I hope it is clear to you all. In this lecture, we have seen what do you mean by combinational logic circuit, what are the various characteristics of combinational circuits, and the different types of adders, full adder, half adder, and full subtractor and half subtractor, and how to implement a full adder or full subtractor from half adder and half subtractor, and also how can we perform the addition of two binary numbers which are having more than one bit using parallel adder. So that's all for this lecture. I hope it is clear. If you have any queries, you can just post it in the comment section so that I can revert back. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.